Good afternoon. Welcome back to Embedded World. I'm Rich Nass with Embedded Computing Design. My guest for the podcast now is Esam Elashmawi. Maui. I'm sorry. I'm sorry. How you doing?
I'm doing good.
And we're all friends. And
Yeah, we've known each other for many years
yes,
too. But
yes, we have. Through many different lives as well. But now we're here to talk about Lattice. First of all, what are you guys doing here at the show?
So Embedded World is an incredible show. It's about showcasing innovation, and what we're focusing on is to showcase our innovation around a few key areas. One is around artificial intelligence, which is a very hot topic.
Yeah, I think I've heard one or two other people mention that here this week.
So we got a lot of real-life demos around AI. We've got live demos around security, which is really critical, especially as quantum computing is coming. We've also got demonstrations around vision. You know, computer vision is getting lots of traction in the world. And also around connectivity. You can't do anything unless you're connected.
Right.
And when you think about those four, you want to connect, you want to be secure, you want to have intelligence around that as well. And so they all fit together.
So it's funny, but what I want to talk to you about is something that you didn't even mention.
Okay.
When I think about Lattice, and I think what makes you guys different is the power levels that you're able to come in at.
That's right.
So let's talk about that. What is it that makes you guys, I'll say better, because I can say that, from a physical perspective, what is it that you're doing differently?
All right, so I'm going to get a bit geeky with you, but I'm going to get to the high level.
It's the geeky audience. We're good.
All right, so in FPGA architecture, there's something called the configuration bit. That's what you program in order to give you whatever functions you need. And when you look at the different companies that build FPGAs, there's two different approaches on how you build that configuration bit. And the way we do that is something around what we call our lookup tables. And there's either a 4-input lookup table or a 6-input lookup table. And the architectural choices are driven by what type of FPGA are you trying to build. And so when you build purpose-built FPGAs like Lattice does for small and mid-sized FPGAs, going up to about 600,000+ system logic cells, 4-input LUT is the ideal choice. However, if you're a company that's going to build multi-million gate FPGAs, the right choice...
Put that into perspective with an application.
So let's say you are doing data center acceleration or AI acceleration. You need a very large density, high performance. The right choice is a 6-input LUT for that type of application. But for what we do, which is really around small to mid-range, you're doing interface, you're doing connectivity, you're doing artificial intelligence, you're doing security,
things at
motion
the edge.
control, things around the edge, or control plane, edge or control plane. 4-input LUT is the right architectural choice. Just do the math. 6 versus 4, right there it's 50% lower transistors, which means you got a smaller form factor and lower power as well. So that's one of the fundamentals. Then the other is our technology choice, a process technology choice. We go for a low power process technology. You add the architectural choice. And then like everybody else, we innovate in the design itself. When you combine all of that, we have a significant advantage in power compared to comparable FPGAs.
And what does that mean when you're building around that device? Is there a learning curve?
Yeah. So you talk about building around the device itself. Yeah, so we provide a lot of IP, software tools, things that help our customers get the most out of our FPGAs. And it's not just the design tools themselves that have power features to help you in our power estimators, but we also invest in what we call software solution stacks. And these software solution stacks are pre-built applications that our customers can use to go implement their function and take advantage of the differentiated capabilities of our FPGAs.
And how much can they actually do with that FPGA? I know people have a lot of preconceived notions. Well, it's just for connectivity, or it's just for this. What can you actually do with that part?
Well, you can do a lot with FPGAs today. Everything from, think about new innovations like humanoids, the motor control, sensor aggregation, security, all the safety capabilities in a humanoid. That applies to factories, factory automation, putting intelligence. You can even do artificial intelligence within your FPGA. For example, if you look at human-machine interfacing, and even on some of the client devices, you'll see that our Lattice FPGA, which is very small, we're talking about 5 milliwatts of power, and, where you can sit there and we can actually determine, are you there? Facial recognition. Is there someone standing behind you? We call that shoulder surfing. There's lots of different types of use models where you can run the inferencing on the FPGA itself. But if you need a lot more performance for your inferencing application, and let's say you want to use an NVIDIA GPU on the edge, well, NVIDIA is a partner of Lattice. We work very closely with them. We have collaborations together, and we do all the sensor fusion and aggregation and pre-processing within the FPGA before we send it to the GPU for edge applications. So there's a lot of things that we can do. The other areas is around security. Security is a really hot topic these days.
Security's hot topic.
Everybody's talking about quantum computing coming out, all of our keys being broken into. The bad actors today are harvesting your data and they're storing it, waiting for quantum computing, and they're going to break all those keys. But Lattice has a leadership in the post-quantum cryptography, and we have the only FPGA out there today that's full CNSA 2.0 compliant with all the algorithms. We announced that actually at a conference in OCP.
And you won a Best in Show award.
And we won a Best in Show. I was just about to get there as well. We won a Best in Show for it today. There's a demo at our booth as well. And so it's really exciting what's happening in security. Frightening yet exciting at the same time that we're actually doing a lot to protect the systems, the industry as a whole with our security solutions.
You got to stay ahead.
You have to stay ahead. It's a constant race. That's what security is about. It's a constant race. And talking about constant race and security, that's one of the beauties of an FPGA. Is something called crypto agility. And what that means, as the bad actors find ways to get in, your FPGA is programmable. You know that for many years. And so we have crypto agility where the user can actually update their cryptography real time and not have to take the system and take it offline and replace it with another one. Crypto agility is something that we have in our FPGA that you're not going to get from a hardened ASIC or
now, is that something you have to build in ahead of time to make sure that you have the logic available on the device?
Yeah, so we've built into our FPGA architecture, not only do we have hardened security block, but we've built within the architecture that hardened security block to be able to leverage the FPGA gates for this crypto agility, which is really important. You know, when the CNSA certified a few algorithms for quantum computing cryptography, and then they challenged the industry to go break those algorithms, and several have been broken already. So this is the beauty again of the crypto agility, where okay, if it's broken, it's fine. We can adjust that within the FPGA to the new standard.
How would you do that without an FPGA?
You respin the silicon, which is very difficult to do.
Interesting. Thank you very much.
Thank you. Appreciate it. Thank you. Always a pleasure to chat with you, Rich.
Thank you.